Okay, so thank you very much to Enrique and the rest of organizers of AmSur, AmSul. Against the will of Enrique, I'm going to talk about one topic which is not related to G2 manifolds. So this is going to be about generalized Ricci flow. And this is based on some joint work with Jeff Streets that we posted on the arXiv on this August. And it's going to appear as a book in the American Math Society University Lecture Series. So let me start with something basic, just recalling what is Ricci flow. So Ricci flow is a natural evolution equation for a metric introduced by Hamilton in '82. So this is this equation tells you that the derivative of the metric in time has to be -2 of Ricci tensor of the metric. And so here, the Ricci tensor is just the usual Ricci tensor of the metric. It's a very natural evolution equation because this is essentially the unique tensor that you can cook up out of two derivatives of the metric in a natural way. So meaning that it's invariant under different reasons. So the only thing you are missing here is maybe a term coming from the metric itself, plus something proportional to the metric. So if we choose local harmonic coordinates at time t0, say, then we can write the Ricci flow equation as some sort of heat type equation. So if we write down what is Ricci flow equation in terms of the components of the metric, this is given by the partial derivative of the components equal to the Laplacian plus lower order term. So this Q is some quadratic expression in G and the first partial derivative of the metric. And then the very basic result by Hamilton and the Turk, which tells you that this equation has to do with some nice geometry on manifolds and can be implemented in any compact manifold, is the following. So if you have a compact Riemannian manifold, then a solution of Ricci flow exists and is unique for some time t bigger than 0 in the interval 0 t with initial condition G0. Okay, so as I said, we have this sort of heat type equation. So morally, what this is doing is to make a curvature uniform along the manifold. So this is similar to the effect of the heat equation on a function, which if you have some metal bar and you have, for example, heat in the center of the bar, then as it evolves with time, then the heat will become uniform on the bar. So similarly, Ricci flow has the effect of making curvature uniform as t goes to infinity. Well, this is almost correct, but actually, what may happen is that in different regions of the manifold, the metric may evolve to very different constant curvature models, and this ends up breaking maybe the manifold into pieces. So this is the typical picture about Ricci flow with surgery developing singularities. And if you are lucky and with Ricci flow on 3 manifolds you are, then this device is going to detect the topology of the manifold. So this is a picture of a sphere decomposition of a 3 manifold in the work by Hamilton and Perelman. Okay, so this great idea by Hamilton of putting a metric on a manifold, letting evolve and see how singularities see the topology of the manifold was implemented by Perelman 2002-2003 to solve the geometrization conjecture by Thurston on 3 manifolds. And something which maybe is not so well known to some people is that Perelman brings in some ideas from physics when doing his work, in particular statistical physics and the theory of 2-dimensional sigma models. So this introduction aside, our talk is about the generalization of Ricci flow, which is motivated by the theory of 2-dimensional sigma models in physics. So these are the equations that I'm going to consider. You fix a manifold, I'm going to assume typically that it's going to be compact, and a cohomology class in this manifold in degree 3. Then the generalized Ricci flow is defined for a one-parameter family of pairs given by GT, a Riemannian metric on the manifold, and BT, a two-form on the manifold. And these are the evolution equations of the metric and the two-form. So here I have to explain something. So Ricci is the Ricci tensor of the metric, depending on T. I'm not going to write down the dependence on T on the right-hand side, but it's there. So this is the Ricci tensor. So this term here is like usual Ricci flow. And then here I have a quadratic expression on H. So what is this? So first, H is a family of closed free forms given by deforming the initial free form by D of BT, D of the two form. And this H squared is a symmetric 2 tensor cook up out of 2 copies of H and a contraction with the metric like this. This is written in components. Okay, so this is as for the evolution of the metric. Then evolution of the two form is given by minus the adjoint respect to of the exterior differential with respect to the metric, which again by taking an orthonormal basis for the metric at time t is given by this expression. Okay, so any questions about the equations so far?
So what are models? Sorry.
Yeah.
What are models?
Can you say it again?
Oh, sigma models. What is this?
Okay, let me explain this in the next slide. So there was another question, I think.
I was going to. So should I think of B as the B field and H as the H flux?
Yeah.
Or?
Okay. Let me explain this in the next slide. Okay. So now we have if the equations are okay. Let me go for the motivation. Okay. So how do these things appear in physics? Okay. So what is a two-dimensional sigma model? This is a physical theory that you construct out of some background geometry, which is given by a manifold, a metric. I'm going to assume which is Riemannian. That is Riemannian and a two form. And then fields in this theory are given by maps from a surface into the manifold. The Lagrangian for this theory has 2 bits. So this is sending one of these maps from sigma to m to the following quantity. So the L2 norm of the differential of the map plus the integral over the surface of the pullback of the B field. Okay. So in answering Jason's question, so yes, the H is going to be the H flux. If I think of my of the critical points as trajectories for a one-dimensional object or a string, if I'm talking about a string theory. Okay, so I hope this clarifies the other question about what a sigma model is. So what is the meaning of this Lagrangian of this action? Well, there is an analogy that you can think of, which is the analogy with magnetic geodesics on a Riemannian manifold. So if you have a Riemannian manifold, you can cook up a deformation of the geodesic equation by prescribing an exact two form, which is thought of as a magnetic field. The potential, which is a 1,4, is used to cook up some natural functional on curves from an interval into the manifold, thought of as trajectories of point particles. And this is given just by the L2 norm of the derivative of the curve plus the pullback of the 1,4 into the 0,1. So this is some sort of a higher dimensional analog of this picture for magnetic geodesics. Okay, so how does this generalized Ricci flow appears from this picture? Well, mathematically this is not so clear, but what physicists tell us is that they quantize the theory, writing some sort of path integral, and then they need a device called the renormalization group flow implemented on the coupling constants of the theory, which keeps track of the change of scale. And here, I mean, coupling constants. Yeah.
Sorry to stop you. I quite like the story of the magnetic path. So can you just explain what's the trajectory there? So it's a charged particle in a magnetic field. So you have a free part, which is its inertial movement, and then.
Yep.
Okay.
Yep.
Cool.
Yeah. Yeah, and then the D field here, the 2 form plays the same role, but for a string instead of a 1-point particle. Yeah.
Cool. Thanks.
Okay. So this renormalization group flow physicists tell us that it makes evolve the coupling constant, but coupling constants is anything that you put in terms in front of the fields in the Lagrangian. So here the coupling constants are our tensors, are the metric and the B field. So when they write down what is the renormalization group flow, they find these equations, which are precisely the equations for generalized Ricci flow. Okay. So there is one caveat, which is that when they quantize physicists run into trouble and they need to modify the functional by introducing an additional field that they call the dilaton field, which is a function. And this function also evolves with time, has its own equation for evolving, and evolves by this very weird quantity. It evolves by minus scalar curvature plus 1/12 norm square of h minus 2 Laplacian plus norm square of the gradient. Okay, so far so good. Physicists now tell us that the stationary solutions for the flow which are closely related to conformal field theories, are critical points of a natural action, which they call the low energy string effective action, given by this formula. So you see the Lagrangian, so the integrand, is the same thing which appears on the right-hand side of the evolution equation for the dilaton field. And here you are doing some additional thing, which is to modify the volume by this e to the minus f. Well,
sorry.
Yep.
That minus Laplacian there is like a backwards Laplacian. That doesn't put some trouble into the existence of the equation or something like that, because you have df dt equals, forget about the rest of the things. You have minus 2 Laplacian of f, right? And that's sort of a backwards Laplacian. And that might put some trouble into the what's going on.
Yeah, that's a good question. I may have, okay. There are two. No. This is the right thing. Yeah, this is the right thing. Yeah, actually, let me comment further on that. But the thing is that this is not the right equation for the theory of generalized Ricci flow. So when you do theory for generalized Ricci flow, you do not think of, or you do not use this evolution equation. You use some other equation, which is like is the equation that you need for flowing by generalized Ricci flow, keep the volume constant for the function f. So yeah, you may be right. I didn't think of that. And the thing is, yep.
Perelman is something very similar, actually, right?
Yeah, but he's not using the same. He's not using the same equation. He's using a different one, which is the one which we use in the book as well.
Yeah, but he also have this minus Laplacian for the dilaton, or however you call it. Yeah. Anyway.
Okay, I don't remember now, but okay, sorry. Okay, so this action functional can be written in a different way by integrating by parts, and you may recognize this from Perelman work if you are familiar with that, because this is the same formula that I wrote before, just after integration by parts, and this is Perelman energy functional in his work if you drop the term given by the norm squared of h. Okay, so all this was just to motivate the equations, but what I'm going to see from now is going to be more geometric, but the main message up to this point is that there are several natural features or natural tools in the theory of Ricci flow itself, which appear from this physics setup. And we're going to consider the most general equation which physicists consider in this story about two-dimensional sigma. Okay, so
Mario, if I got this right, then Perelman's case is the free case, right? Before you switch on the magnetic field thing.
Yeah, you can think of it that way. Yeah.
Okay.
Yeah.
So you're at least as complicated as Perelman's work.
Yeah, but some things are very similar to what.
That's very brave.
Some others
okay,
are.
cheers.
I will show you. Okay, so beyond this physical motivation, which is interesting and inspiring, but it's not math. What we expect is that generalized Ricci flow provides a natural and fruitful tool for other classification problems in higher dimensions, like, for example, the proposal by my collaborator Jeff Streets on the classification of complex surfaces.
Can I ask a question?
Yeah, sure.
So is the generalized Ricci flow equation or negative gradient flow of that functional f which you introduced earlier?
Can you say it again? If it is the...
So is it like a negative gradient flow on the space of metrics times functions times two forms on M of that functional f? Just
Yeah,
like in
yeah.
Okay.
Yeah, for the right choice of it, yeah.
Yeah, okay. And so do you have to do you need to normalize the weighted volume to be constant here as well?
Yeah.
Okay.
Yeah,
okay, thanks.
That's true. So naively, if we have this proposal, naively, generalized Ricci flow is more flexible, so we may have more chances to geometrize a further class of manifolds, a bigger class of manifolds by using this tool. So can we actually use it to find some canonical geometries in a broader class of manifolds? So let me start with something very simple, which is what happens if I just consider stationary points of the flow. Okay. So can we geometrize more manifolds with stationary points of generalized Ricci flow than for this Ricci flow? So for Ricci flow, the stationary points are given by Ricci flat metrics, so in particular Einstein. And then we have this theorem, this classical theorem by Berger, which is a generalization of, this is a particular case of the Hitchin-Thorpe inequality. So you have a compact four-dimensional smooth manifold M, and it admits an Einstein metric, then the Euler characteristic has to be bigger or equal than 0. And furthermore, if the Euler characteristic is 0, then this happens if and only if G is flat. Okay, so let's take S3 cross S1. This has 0 Euler characteristic, and therefore M does not admit any Einstein metric, because otherwise by the Killing-Hoff theorem, we would have that the universal code would be R4, okay, by Berger's theorem. Okay, so S3 cross S1 does not admit stationary solutions of generalized Ricci flow, of Ricci flow. So for generalized Ricci flow, the stationary points are given by the following equations, with H a closed 3-4. So one remark is that these equations correspond to vanishing Ricci tensor for a different connection than Levi-Civita. It's a connection with total skew symmetric torsion given by this. So if I were in the set of Hermitian geometry, this would be the bismuth connection. Okay. So this is nabla plus a half G minus 1 of H. So H is the torsion after raising 1 point. So one small observation related to our previous example on S3 cross S1 is that the tensor H squared is semi-positive, and therefore morally the previous equations may have solutions on manifolds which have some positive curvature. Okay, so let me go for actually the example then. So if we take S3 cross S1 and identify this with SU2 cross U1, then if you consider generators for the Lie algebra, E1, 2, 3, 4, satisfying these relations, and you take H to be minus C1 to 3, so this is just the pullback to the total space of the Cartan free form on the SU2 factor, then you can define a invariant metric by taking just E1 squared, E2 squared, E3 squared, E4 squared. Then this metric is a product of invariant metrics on the simple group SU2 and the abelian group U1, actually of being invariant metrics. And therefore it follows that nabla plus is flat. So this is a general fact about simple Lie groups endowed with the invariant metrics and this nabla plus connection. Okay, so we have seen that therefore there are manifolds, very simple four manifolds, for which we have solutions of generalized Ricci flow, stationary solutions of generalized Ricci flow, and not stationary solutions of Ricci flow. Okay, so what about non-constant solutions of generalized Ricci flow? So let me state this theorem by Jeff Streets, proved this in 2008 in a paper in Journal of Geometry and Physics. So the theorem states that generalized Ricci flow exists for short time. So if we have a compact Riemannian manifold with closed free form A0, then generalized Ricci flow has a unique solution for time 0t with t bigger than 0, and initial condition G0, H0. So here I'm saying this is the same as saying that B0 equals to 0. Okay, so these are the equations. And let me comment very briefly on the proof, because some ingredients will appear later. So what you do to prove this thing is to follow essentially the proof by the Turk. So apply the Turk method. So you consider a gauge fixed version of the flow for GH. So why do you do that? Well, Ritchie flow, as well as generalized Ritchie flow, has a huge group of symmetries coming from diffeomorphisms, essentially, right? So doing this gauge fixed version of the flow is trying to kill the kernel of the linearization. Okay, so you consider this gauge fixed version of the flow for the pair G and H. So I'm not going to deal with the two form. I'm going to deal with the pair metric and free form. So up to here, it will be just generalized Ritchie flow, the evolution equation for the metric, and then I'm adding this Lie derivative of the metric, and then here I evolve by the Laplacian plus Lie derivative of H. Okay, so what is X? X is prescribed, and it's going to be given by this time-dependent vector field is going to be given by G minus 1 of the trace of the difference of the two Levitch beta connections. Okay, so once you do this, you get a parabolic flow, a parabolic equation, and therefore you are automatically you can automatically get a short time existence.
Mario, so this is scaling. What is the scaling? This is scaling isometries, right? That's diffeomorphic. Is this scaling all diffeomorphisms? What is the scaling? What is the Turk trick killing here? What's the ambiguity?
It's not isometry, it's bigger than that.
Yeah, it's more than. Okay. Anyway, just asking if this has a natural interpretation or if it's just X is just what it has to be. I mean.
Well, I'm going to give an interpretation of what X is in 10 minutes.
Okay.
If you allow me.
Cool. Okay.
Okay. Then the way you get the short time existence for the generalized Ritchie flow then is to integrate on the evolution equation once you have the H field. So once you have the free form, you just integrate in this equation here. Okay, so this is the way you get short time existence. Let me give you an example which shows very clearly what are the qualitative differences between Ritchie flow and generalized Ritchie flow in a very simple manifold, which is the three-dimensional sphere. So consider the three-dimensional sphere endowed with a round metric, okay, with constant sectional curvature 1. Then for any one parameter family of constants lambda t and eta t, we're going to take these ansatz GTHT for the generalized Ritchie flow. So then this is just the rescaling of the homotopy of the metric and the rescaling of the volume form on the manifold. Okay, so with this ansatz, generalized Ritchie flow implies that eta t equals eta 0. So eta t is constant. This is just a manifestation of the fact that the cohomology class of the free form does not change in time with generalized Ritchie flow. And this generalized Ritchie flow then reduces to an evolution equation for lambda, which reads like this. So we have essentially two cases. One case is when eta 0 equals to 0. This corresponds to no volume form, so no free form. Therefore, we are in the case of Ritchie flow. In this case, we simply obtain that the partial derivative of lambda is -4, and we have a solution of the flow in the interval 0, lambda 4 divided by 4, given explicitly by this. So we observe one of the natural features of the classical Ritchie flow, which is that the round sphere rings at constant rate homothetically to 0 at finite time. Okay, so let's see now what happens if I turn this free form on. So if eta 0 is non-zero, so when the free form is present, there is a unique fixed point so a unique stationary point for the flow given by lambda equals eta 0 divided by 2. And this is attractive in the sense that for lambda smaller than this quantity, one has that the derivative is bigger than 0. and for lambda bigger than this quantity, one has that the derivative is negative. So one exercise that one can do is to prove that for any initial choice of lambda, the solution of generalized Ricci flow of this ODE exists on 0 infinity and converges to this value. Okay, so then there is a striking difference between generalized Ricci flow and Ricci flow. So once we have H present, then this is attenuating the otherwise singular behavior of the Ricci flow. And then this finite time singularity that we observed in the previous slide becomes now a flow with infinite existence and convergence at infinity. Okay, so any questions so far?
Perhaps
yes,
I have sorry, can I ask something?
Yeah.
Yes. You mentioned that the sphere it shrinks at finite time, but when you take the normalized Ricci flow, this doesn't happen. So this equation that we are seeing, it can be understood in somehow like an uniformization of some quantity, like it preserves, for instance, like the normalized Ricci flow preserves volume.
Yeah, I agree. Actually, we make a comment on the book about it, but I agree that if you are like zooming in, then you can understand that the Ricci flow does not develop a singularity in the free sphere. But this simple example shows that if you consider the manifold as such without any rescaling, then you're going to be, I mean, generalized Ricci flow is going to develop very, very different features than the Ricci flow itself. Okay. I'm not claiming to make any, I'm not trying to make any profound claim, but just showing some of the basic features of the flow. So what is going to happen in higher dimensions, which is something very different from Ricci flow, is that if you have a direction in the manifold, which is detected by the free form, meaning that the contraction of this vector or this vector field with the free form is non-zero, then this direction is going to be is not going to collapse as time goes to infinity in the manifold. So there are very different features of the two situations. Okay.
Thank you.
Okay, so let me pose a small conjecture, which is in our work, which is related to the previous example. So suppose that G is a compact semi-simple A group with invariant metric G infinity. So they've been given a left invariant metric G0 and taking this free form. So this is just the Cartan free form. Then the generalized Ricci flow with initial condition G0 H0 exists for all time and converges to the invariant metric and this choice of free form. So let me give you two examples, one example and one exercise. So the example is G equals to SU2 identified with free sphere as we saw it before. And in this case, if you take G0 equals to lambda G infinity, then this corresponds to the previous case that we saw in the free sphere. And a more delicate exercise to do is you can prove the conjecture for SU2 and G0 diagonal left invariant metric in an orthonormal basis for G infinity. Okay. Just to, I know that some people in the audience like about flows in Lie algebras, so this is a nice thing one can try to prove. Okay, so let me move on and show you some natural geometric framework in which generalized Ricci flow has its natural life. So so far I just motivated the flow by introducing or by talking about this physics of two-dimensional sigma models, but actually generalized Ricci flow has a very natural meaning in the theory of generalized geometry by Nigel Hitchin. So this beautiful picture of generalized geometry was introduced by Hitchin in 2002, and in his words, the basic premises of generalized geometry are to replace the tangent bundle of a manifold by the tangent plus the cotangent bundle. And the second one is to replace the Lie bracket on the manifold by a suitable bracket called the Dorfman bracket. Okay, so let me go into some details of this. So you take a smooth manifold M, you take tangent plus cotangent, and this has a canonical pairing given by the natural pairing between vector fields and one forms given by this, and a natural bracket called the Dorfman bracket, which is not antisymmetric, but satisfies a natural Jacobian entity. So it is given by this formula in terms of natural operations on the manifold, like Lie bracket, Lie derivative, and the zero differential and contraction. Okay, so the bundle tangent plus cotangent endowed with this metric has a structure group O and N. So this is a metric with a split signature. And symmetries given by an extension or an enhancement of the group of diffeomorphisms on the manifold. This enhancement is by closed two forms. So a closed two form acts by the so-called B field transformation, shifting X plus T, a vector field plus a one form, by this formula, given by like contraction of the vector field with it. So there is a twisted version that we are going to use, which is given by this more abstract setup. So one has an extension of the tangent plus the cotangent bundle. These are all smooth bundles. E has a bracket and a pairing, which are some abstract guys, and satisfy some axioms, which are the ones which are satisfied by this explicit structure. Let me not go into the axiomatics, but let me just tell you that this has a split signature metric, this E, and if you choose an isotropic splitting, then this E is isomorphic to tangent plus cotangent with the same metric as before, and a bracket which is now twisted by a free form. So it's the same bracket I had before here, and a twist by a free form. And the class of the free form in the degree 3 cohomology of the manifold parameterizes isomorphism classes of these E's. This is called the Severa class. Okay, so pushing forward this proposal by Hitchin of doing geometry on tangent plus cotangent, one can consider the notion of metric. A generalized metric is a reduction from O and N to its maximal compact given by O(n) times O(n). And this is the same as a rank N positive definite subbundle inside E. And another way of seeing this is as an orthogonal endomorphism from E to E, such that G squared equals identity, and contraction of this with the ambient pairing is positive. Okay. So if we choose an isotropic splitting for E as before, then this is going to be as a bundle just tangent plus cotangent with this twisted bracket for some H0, which is closed. I have chosen one isotropic splitting. And then I can write my B plus, my metric, as the graph of a two tensor, which I decompose into the symmetric part, which is this G, and a skew symmetric part, which is a 2-4. And actually, one can show that this G has to be a metric, has to be a Riemannian metric. One important observation is that a generalized metric has itself a preferred splitting. So if I have chosen one splitting, if I have chosen one particular presentation of my E, then the generalized metric gives me a different one for which the B field is 0. And therefore, it also gives me some particular representative of the free-form class given by the H0 plus DB. Okay, so with these very basic generalized geometric tools in hand, I want to state a theorem, but let me before ask if there are any questions. No?
I don't want to ask something too complicated, but can one view this H as the curvature of a gerb? Is there some kind of gerby thing going on here?
Yeah, if the cohomology class is integral, you can do that. Yes, that's true. Yeah.
Thanks.
Okay, so let me say this term. I have said this in a very pedestrian way, but I didn't want to make things complicated. The nice things are in the proof, but let me say it this way. Okay, so this is due to several people in several papers, I guess. So Sebera Balagh, myself, Jurko Vysocky, and myself and Streets. So the statement is that the generalized Ricci flow, as I have introduced before, with this H being this free form, and this action which appears in the sigma model that I'm going to call the generalized Einstein-Hilbert action, these two things are preserved by the group of automorphisms of the exact Courant algebra. Okay, so this is just generalized Ricci flow, as I said it before. Let me comment on this thing because here there is a new ingredient. Okay, so this depends on the data of a generalized metric, a metric, and a two-form, but there is also this function there. Okay, and this quantity has appeared before when I talk about these sigma models. Okay, these are some natural expression which appear in the physics. Okay, so this is not so obvious because firstly the group of automorphisms is a semi-direct product of the group of diffeomorphisms, but suitable is of a subgroup of diffeomorphisms which is preserved in the cohomology class of the three form by closed two forms. Okay, I was planning to share my screen here and write something, but I don't know if I dare with Google Meets because I always use Zoom. Do you think it's easy to do that, or I'm going to get crazy?
Nothing is ever hard for the brave.
Okay, let me not do it.
Okay.
Anyway, so I can try to do it. You see my screen, right?
Yes.
Do you see Paint now?
Yes.
Oh, yeah, that's great. Okay, let me do it then. I do it. Yes. Let's do it. Okay, so I have tangent plus cotangent of a manifold. I have this H0, which is a free form on the manifold, which is closed. And I have this weird bracket that I'm not going to write again. But if I call this E endowed with the full structure, so E is going to be this thing, the pairing, and the H bracket, then the automorphisms of E are given explicitly as follows. These are given by pairs phi B, where phi is a diffeo on the manifold. B is a two-form on the manifold. And then I have this equation. This should be bar phi. Phi star of H0 minus H0 equals to D. Okay, so this is the phase of this automorphism group. Okay, so it's not so obvious that this thing is acting, preserving all this structure. Okay, and I didn't tell you how it acts on generalized metrics, but let me skip that. Okay, good. So let me comment on the proof because this is where the geometry really is. So this looks like okay. I have this weird group. I'm acting on this full structure, and I'm saying that all these things are natural in generalized geometry. Our proof is inspired by a beautiful paper in the physics literature by Waldron, Coimbra, and Strickland Constable, and there are other proofs by Sebera Balagh and Jurko Vysocky. But let me comment on what we do. So you need to introduce a device called divergence operator in order to talk about curvature in generalized geometry. So a divergence operator is an R linear map which takes sections of the Courant algebra into smooth functions and satisfies this sort of Leibniz rule. So here pi is the anchor map. So it is the projection of tangent plus cotangent into the tangent map. Okay. So the idea is that generalized geometry is cooked up in terms of tangent plus cotangent. So everything should be, you should be able to phrase everything in generalized geometry in terms of the bundle of frames of tangent plus cotangent, which is an ONN bundle. And therefore, morally, there is no way of implementing conformal geometry in there. So these objects are helping to do this conformal geometry on generalized geometry. So let me give you one example, which I'm going to use. If you have a generalized metric, G, then recall that this big G, it uses a usual metric on the manifold and a specific isotropic splitting. So a specific way of detecting what is the vector field and the one. So then the divergence acting on X plus C, the divergence associated to this G, so the remaining divergence, let me call it, is just the remaining divergence associated to the remaining metric. So you can write it down either as trace of nabla G of X or as Lie derivative of the volume divided by the volume. Okay, so now how do you prove this theorem about the naturality of all these quantities? Well, the proposition or the result is that associated to a pair generalized metric and divergence operator, there are curvature quantities. So there is a generalized Ritchie tensor, which is a natural endomorphism in tangent plus cotangent. And there is a generalized scalar curvature, which is a smooth function on M. And then with these curvature quantities in hand, you can write down generalized Ritchie flow and the generalized Einstein-Hilbert action in a very natural and beautiful way, which is this thing, which really resembles like Ritchie flow, but in a different geometric setup. And this is the generalized Einstein-Hilbert action as some sort of Einstein-Hilbert action for a modified volume. Okay, so here this div operator is not the remaining operator the remaining divergence that I wrote down in the example, but is deformed by the function. So this is the way functions appear in generalized geometry by deforming the divergence operator. So you can see that because this satisfies this Leibniz rule, and this thing is also, these two things together are also satisfying the Leibniz rule. So in different words, if you give me two divergence operators and subtract them, then what you get is a smooth section of the current algebra.
Mario.
Yep.
Are these divergences still formally adjoint to some differential operator of order 1? So can you form Laplacians with them and do cool things?
Okay, this is a good question. Actually, so this is our approach to this question, and it's motivated by this paper by Waldron et al. The approach by Severa and Balach, what they do is precisely considering some sort of Laplacian operator acting on functions or acting on half densities. And this is associated to a divergence operator. So I think what you're saying is right. And calculating sort of the Laplacian associated to the divergence will give you this other definition for the generalized scalar curvature that is implemented by Severa and Balach.
Cool.
Yeah, in fact, what Enrique was asking is that you're taking the adjoint with respect to the modified volume, and then you get what he's saying, right?
Okay, yeah.
That's right. Cool.
Yeah. Okay. So what we have this other quantity, this Ritchie, depending on a Riemannian generalized metric and a divergence operator. So what if we modify this generalized Ritchie flow equation, which depends on the remaining divergence, by putting an arbitrary divergence? What is the meaning of this thing? Well, the more general flow for arbitrary divergences, what is keeping track of is natural gauge fixed versions of generalized Ritchie flow, where the gauge fixing is now given by automorphisms of the current algebra, so if you want generalized diffeomorphisms. And there is an interesting comment here. You see that even bits in the theory of Ritchie flow appear or accommodate naturally into this picture. So for example, if you consider the gauge fix generalized Ritchie flow appearing in the third streak, which was given by this thing, recall that the vector field I was using to gauge fix was this thing, was G minus 1 trace of the difference of the two Levi beta connections. But this is nothing more or less than the difference between the two divergences associated to the Riemannian metric. Okay. So all I'm saying is that I think there are bits even of the Ritchie flow theory which are going to be better understood with this picture probably. Maybe only at the formal level, but who knows? Maybe more. Okay, and this leads to some natural notion of Ritchie soliton and etc. So if you want to read more about this, you can go into the book. But let me now move to something else. Okay, are there any questions so far?
Does this play nicely with generalized Kähler geometry?
Oh yeah. So Streets and Tian introduced a beautiful flow called the generalized Kähler Ritchie flow, and actually what they prove is that generalized Kähler Ritchie flow reduces to generalized Ritchie flow. So if you have a solution of generalized Kähler Ritchie flow, in particular, the metric and the free form are going to satisfy the generalized Ritchie flow. So yeah, it's like the perfect analog between like the relation between Ritchie flow and generalized Kähler Ritchie. Ritchie flow and Kähler Ritchie flow. Yeah. Thanks.
Great.
Thanks for the question. Yeah. Okay, let me move to T-duality. So why I stated this weird theorem? So the theorem doesn't seem to say much. It's just, I discovered this like B-field symmetries in the picture. But we knew that from physics. So what this is going to give us what this is going to give for us is a way of proving that the gauge-fixed versions of generalized Ritchie flow are invariant under T-duality, which is a natural symmetry which appears in physics. So T-duality is an equivalence between two-dimensional superconformal field theories. But whatever this means, in a limit, T-duality has some geometric shadow, and this was discovered by Busser, Rosek, and Berlin in 1987. By the way, Henrique, how much time do I have? Like 2 minutes or?
We could do 2 minutes plus 6 minutes plus 4 minutes questions, and then but there were lots of questions during the talk, so just
may I have 5? May I have 5 minutes or is 2 minutes?
Yeah.
Okay. From 5 minutes.
And we can save all the questions for once you're done. Okay.
Okay. Thank you so much. Thank you. Okay. So T-duality has this geometric shadow discovered by the physicists in the 80s. And the beautiful thing is that it exchanges solutions to suitable geometric PDE in manifolds with different topology. Okay. So what I'm going to consider here is a very basic situation where the torus fibers are actually given by a principal. The fibrations are given by principal torus bundles. And let me start with an example. Okay. So take the 3-sphere, so the whole fibration, fibering over S2. Okay, and I take the round metric on S2 and the associative volume form. I choose a connection 1 form for this fibration of this U1 bundle, whose curvature is the volume form on the 2-sphere. And I define this family of metrics depending on two constants. Okay, so this V is rescaling the circles on the whole fibration. So let's say that we try to solve Ritchie flow with these ansatz. You can do that. Then if you write down what explicitly Ritchie flow is, yes, you solve Ritchie flow. Then this transforms into this system of ODE. And then you can show that BH go to 0 in finite time, and this S3 is shrinking to a point. Okay, this is a slight generalization of the example that we showed before in the case of the 3-sphere, where I'm rescaling differently the base and the fibers with respect to the whole fibration structure. Okay, so what physicists tell us about this simple example of Ritchie flow is that there is another flow in a different manifold with different topology, which is kind of paired to this one. So what they say is that this solution of Ritchie flow is exchanged via this T-duality with a solution of the gauge-fixed generalized Ritchie flow on S2 cross S1. And these are the equations, okay, for this gauge-fixed generalized Ritchie flow. Where here I'm changing the equations that I had for generalized Ritchie flow by these natural quantities, depending on the gradient of a function that physicists interpret as the dilaton field. So actually, this T-dual solution is completely explicit. They give you the formula. They tell you in coordinates, I can cook up what is the formula, and you can do it here and globally. So this is the formula for the T-dual metric. And here observe that the initial metric is changing the size of the fibers from B to 1/B. Okay. And then you can write down what is this gauge fixed generalized Ritchie flow on S2 crosses 1 with these ansatz, and you end up with this system of ODE. Observe that this is just the same thing I had before, changing B bar by 1/B. Okay. Okay, so can we explain this thing? Can we give an explanation of why this is true? This is just told us this is true, but why it's true? So let me go for this definition by Bognet, Eflin, Hanabus, and Matai. So if you have two principal torus bounded over a common base, then and two closed free forms which are invariant, I consider this fiber product on this diagram, and I'm going to say that MH is T-dual to M bar H bar if there exists a two form which is invariant on this corresponding space, which is non-degenerate on the fibers in a suitable sense, and trivializes the difference between the closed free forms. Okay, so this is the definition. A basic example of T-duals is the Hopf vibration with H equals to 0, as we saw before, and M bar taken to be S1 cross S2 with H bar minus the volume element in the S1, which the volume element in the S2. Okay, so the calculation that these are T-duals is a very simple exercise, so let me skip this because I'm running out of time. Okay, so this is the theorem I wanted to state. So let MH, M bar, H bar be T-dual pairs. So this is with the streets. Then if there exists a solution of an invariant solution of the gauge fixed generalized Ritchie flow on M with this cohomology class, then M bar, H bar admits a T-dual solution with the corresponding cohomology class in the T-dual. Okay, this has been proved by several people, and I'm going to comment on that in a minute. But what is new and didn't seem to be in the math literature is this second part. So if you normalize the volumes of these functions to be equal on the initial manifold and the T-dual, one has that the two generalized Einstein-Hilbert actions agree along the flow for the given solution and the T-dual. And this is the formula for the function. So there were physical proofs by brutal calculations and explicit formula by Buscher-Rosek of the first fact, and then by Berhu, Hall, and Orting of the second fact. An interesting point here is that physicists check this. For example, Buscher checked that the sigma model action, so the action on fields given by maps from the surface into the manifold, this action is invariant under T-duality. But the way they cook up this other functional is via a Feynman diagram expansion. So this second bit in the theorem is a sort of quantum effect of T-duality. And then there were math proofs of one using general geometry by Severa Balach, myself, and Jurko Vysotsky. But two seems to be okay. And just to finish, so this is the same theorem. I just erased this last line for having a bit more of a space. The proof is a consequence of two things. One is a theorem by Cavalcanti-Gualtieri, which tells us that T-duality is an isomorphism of Courant algebroids after reduction. The other one is that all the natural quantities which appear in this theorem, like generalized Ritchie flow, gauge fixed generalized Ritchie flow, and the integrand of this generalized Einstein-Hilbert action are natural quantities in generalized geometry. So these are like preserved and then generalized diffeomorphisms. And the other thing that you need is a dilaton shift formula which was observed by physicists, and I proved in this paper in Advances in Mathematics last year. Okay, so I finish here, and thank you very much for your attention.
Great, thanks. Have you got any more questions for Mario? Because otherwise, I may have one.
Yep.
Is everyone sure? Okay. So Mario, as you know, we've known each other for a long time. I only have one question, which changes every year. I just ask the same question, regardless of the context. so let me do this here.
It's a good strategy for showing up in seminars.
No, it applies everywhere. It's
Showing up
universal.
in
It's a
seminars.
universal question.
Yeah.
Your toy model here has been the hop vibration, right?
Yep.
And then by fiddling with the volume of the base and the length of the fibers, you get an ansatz for your generalized Ricci flow, and then you can find in that case, for instance, what is the dual manifold and how the dual flow performs there. What about you think much more generally in terms of these contact Calabi-Yau manifolds, right? They exhibit the same sort of features. They are Sasakian manifolds, they're circle fibrations over a Calabi-Yau base. In the 7-dimensional case, for instance, they have a natural invariant 3 form. So I believe they have all the ingredients that you need. And a very interesting question would be, what is the dual manifold in this case? Because it looks like it's something, the topology of which is more trivial, right? So in the case of the hop fibration, you get something which is S2 times S1.
Is there a natural free form there in the geometry? Closed free form?
Yeah. At the very, there are several ones. For instance, there's the contact form wedge, it's derivative, right? And you can do, or in the case, when the base, the Sasakian manifold has a Calabi-Yau base, then you even have a G2 structure. There's lots of interesting 3 forms, which are natural, which are S1 invariant. So I believe it would be interesting to look at what their duos have to be. And they're associated to Candelas's, that list of Calabi-Yaus he wrote down one day, which are interesting for string theory. Basically, for each of them, you have a Sasakian manifold with that base. So they're good 7-dimensional analogs. They're good odd-dimensional analogs of Calabi-Yau manifolds. Okay. And
there is not much I can say about that. So one thing is that certainly regarding the topic of this lecture, one can try to, if there are like natural cohomology, degree 3 cohomology classes in these manifolds, one can try to see what is the behavior of this generalized Ricci flow in them, and also whether you have like a T-dual solution somewhere. Yeah, but I will have to study these geometries. I am not very familiar with them.
Well, if you want, I'll be very happy to discuss it. You certainly have non-trivial elements representing classes in H3, which are natural and which one might look at. Yes.
Okay.
So, good. Any more questions for Mario?
So
in that case, go ahead, Jason.
I want to if you have, so you mentioned S1 times S3 at some point for your generalized. So I mean, I guess you could think of that as an S1 bundle over something. Is there a natural T dual to that?
Yeah. So this, these metrics in S3 cross S1 are a self-T dual. But you can put parameters in those metrics, and actually it's very interesting because these are very, very special solutions of this Ritchie Laplace equals to 0, which are interacting with complex geometry. So you can think of this as a hop surface. Right. And then what happens is you have that it's not only that the Ritchie of Laplace is 0, these things are flat. And therefore the holonomy is reducing to SU2. And you can see explicitly what is a parallel spin-off for this Laplace. So if you put into place the complex geometry, you are going to see a non-trivial behavior of the spinor under T-duality. So you are not going to see it from the point of view of the metric, say, but the spinor is going to rotate in a very natural way, very similar to what happens for hyperkähler. These are locally conformally hyperkähler examples.
Yeah. Right, but there's no change of topology this time.
There is no change in topology. This is due to this H. So in the case that I was considering just the S3 factor, then I had H equals to 0. And
Right.
what happens is that the combination of the pair given by the vibration and the freeform, this combination of two things is preserved somehow under the T-duality. So the first 10 classes of the vibration are exchanged with the cohomology class of the freeform and vice versa. So this means that here you have a balance situation where you have this S3, this Hopf vibration over S2 with first 10 class equals to 1. And on the other hand, you have this H, which has also some natural cohomology class, and it is in a way which is preserved under the T-duality. If instead you take the H to 0, then you will see a change in the topology after the T-duality.
Great, thanks.
All right. Can we call that the last question? And thank Mario again, please.
Thanks.